So I gave you a really short introduction to the Salvage project this morning. What this presentation will be about is the sort of currently last running work package 5, which deals with integrating sort of different detection tools that Salvage has been looking at into sort of a, let's say, joint risk assessment solution or so. And so there's a couple of assumptions behind sort of how we see the world, or what we kind of assume to be the case. First, let me quickly recap. Salvage is mostly looking at distribution grids, and specifically distribution grids with a relatively large number of distributed energy resources. So we make the case, or we would like to make the case for a real-time tool, or the need for real-time analysis of the current situation of the grid with respect to multiple aspects that the grid has. Let me reformulate that. Sorry, I got stuck there. Maybe I start at a different point. We had, as I presented this morning, we had sort of three domains in which we looked at sort of analysis tools for smart grid cybersecurity. One is trying to look at, actually quite similar to what you just presented, sort of model-based intrusion detection by looking at the physical domain based on measurements, then making a cyber vulnerability analysis that tries to determine the probability of an attack or certain types of attacks, and then make an impact analysis. So that is mostly classical power systems analysis work. And so the challenges that you have from these different tools, they give outputs of very different quality. And one of the challenges is to actually combine them, because otherwise it's really, really hard to get an overview as an operator on what to do or how to combine these different assessments that you have. So what if you had such a system, what that could be used for could be both an online analysis, so you could actually find out about the probability of a certain cyber attack being in progress, but also if a cyber attack has happened. And we have one of the examples that I have in the presentation later. We have also looked at cases that are basically difficult to detect before they happen, specifically protection systems. There you could at least use it for quick system restoration, because you can get a good overview of what would be the most likely thing that just happened to you. So what we've been looking at is making an automated tool that works in real time, that looks at sort of runs continuously, that looks at incoming data, and that can handle, to some degree of automation, the dependencies that you have between the different domains. Sorry, I've got some problems here. And so to give an idea of what is meant by sort of cross-domain interactions, this is kind of our, I think, current view, or final view maybe, because the project is about to end, of the three domains that Salvage has been analyzing. That's, probability of an attack, the probability of a DR unit behaving differently than you expect, and the physics of a power system. And so, there's some sort of large lines that are relatively easy to follow. You have if you have an attack on an IT system, then obviously you have the influence that can be exerted on the power system is via the configuration of actuators and control functions that you have access to. The observations that you can make and the detection efforts that you can make about behavior of components of the power system, they of course depends on the sensors that you have. And then you also need to augment this with some observables or predictables that you have from the IT domain. But then you zoom a little bit in, and it becomes a little bit more complex. So we had this general idea in the beginning of the work of what we wanted to do, which was using an approach where we test hypotheses. So the idea was, starting from up here, you would generate many hypotheses, different hypotheses about what is currently going on in the system. Some of them might be complete rubbish or not founded on anything, but you would test it anyway. And you would sort of split this hypothesis up, and I'm getting to that later, into the 3 different domains. Then run sort of the representation of what the system would look like under this hypothesis through the analysis tools that you have, and basically simulate the system under the assumptions of the hypothesis, and then compare that to what you're seeing. And so then you get, a sort of likelihood that you can compare or you can rank. Unfortunately, that's not really easy, because the key is in splitting this. Doing an automated splitting into sub-hypotheses, we looked a bit into that and sort of tried to wrap our heads around that, and that turns out to be really difficult, particularly to do it in a general way. So, so the approach that we had, that sort of we've been following in the end, was to basically build something that we call hypothesis templates, which are at the moment manually generated, and they are trees, but not that contain different types of information. On one side, you have sort of a probability tree. That's kind of a classical approach that you know. But then there's also other information that needs to be exchanged between the different domains. Like, for example, physical information. What current is flowing somewhere? So you have these parallel parts of the tree, and what this hypothesis template basically defines is how for a particular use case the different domains need to interact to come to, and this is what all these hypothesis templates have in common. They have a risk node at the end, which is at the root of the tree, which is, probability times impact or times consequence. So that allows us basically to make, for common types of problems, some templates, and I'm getting to why there are templates in that hypothesis, that we can then compare based on sort of a common sort of quantifier that is the risk in the end. Why are they templates? I should I start with an example. And this is, and I just write it here, this is the dumbest cyber-physical system we could imagine, because SALVAGE, the project, defined a couple of use cases that we thought were most interesting for our work in distribution grids. And we tried to use one or two of them sort of for working on this approach, and we found that this was completely overwhelming. So we needed a simpler system, and so this was kind of the simplest thing that we could come up with that would contain all 3 domains, but where each domain is extremely simple. So I'm very sorry, this is absolutely dumb and does nothing. It's not good for anything, but I think it might be sort of helping a bit to explain how we're thinking. So this is a PV inverter, and there's sort of a network. Let's say that's just a single line, and you have a control computer that you can use to switch that PV inverter on and off, so there's only one function available. We assume the sun is always shining. And then that PV inverter is connected to a grid with an extremely tiny fuse, so that the result of that PV inverter ever switching on is that the fuse blows. So as you can see, this system doesn't do very much, can be really used for much. And so the main advantage of it is that you can easily quantify the damage done, and it's also quite easy to observe that the damage has been done, because you just stand next to the fuse and watch if it blows. So that results in, and I was including that for laughs actually, that results in this tree. Don't try to read it, that's not the point. I'm going to zoom into a couple of points later. But so, yeah, we were kind of surprised how complex. This is a stupid simple system, and the complexity is a bit overwhelming. The good thing is also what we found out, it actually doesn't get much more complex for larger systems, because the complexity is mainly owed to the domain interactions. And so if you have a comparable system that has the same number of domains and sort of similar interactions between domains, then like just a power system that is a bit more real, then you actually get a tree of the same complexity. So that's kind of soothing to know. Basically what you do, I mean, just to, what does this tree do? I mean, it basically calculates the probability of an intrusion based on, well, the theoretical, I mean, the vulnerability that you calculate and what you might observe or what you might have observed from the DR intrusion detection. It then uses a component model to determine the behavior of the device that has been intruded, and then runs that through a power system model to find out what would happen in the grid. And then finally, you basically calculate the consequences, combine it with the probabilities that you've carried through the rest of the tree, and calculate the risk. It's easy, right? So there's one thing that we found out pretty quickly, or yeah, it was a bit of a process, but at some point we realized that, I mean, there's some things that we don't know, and I mean, that has been discussed a couple of times today. I mean, once you have a device that has been attacked, there's many things that you could theoretically do, and you might be able to attach a probability to the different things. I mean, like you might be able to estimate the probability that an attacker switches that inverter on or not, or finds it attractive or not, or so. But that doesn't help you when you need to then run the analysis of the impact on the power system, for example, because you can only do that based on a concrete action. Or at least you cannot, I mean, with present tools, you can only do that based on a concrete action. That's maybe limited that way. So, so we introduced that thing that's called, I'm not sure if you can see that, that's supposed to have a yellow background, but so we introduced this concept of branch points, and I will get later back to why they are a bad idea. That basically are used to generate alternate hypotheses from the template. And so this is how you, this is sort of one of the ways that you can take a hypothesis template and generate many hypotheses from it. In this case, you can generate 2 from it. This is why it's simple. So either the attacker switches the inverter on or he doesn't. But that basically means this whole tree then splits into 2 parts. And you can barely see here that so one half of it is basically grayed out, which is the whole stuff that depends on the inverter being not on. And you basically evaluate them separately. You can calculate separate risks, and then you can compare them. We have a second scenario. I got the 3-minute sign, so I have to hurry this up a little bit. So this is one of the real, I mean, once we had this figured out, we got one of our real scenarios, which is where we're looking at an attacker changing selectivity, or I mean, adjusting the ratings of protection relays in order to change selectivity. What could you achieve with that? You could cause way higher power loss in case of a short circuit than you would without. The problem with this is that, I mean, sort of model-based intrusion detection doesn't work really well until it has happened, because, yeah, it's a protection device. It doesn't work unless something is wrong. So, but you could use that here for post-mortem, actually. And then, so this is the resulting tree that we get out of this. And as you can see, the complexity is actually not much higher. What is different, though, is that here in this one, now you have 2 branch points, and sort of they're kind of hierarchical. And there you can see the problem with the branch points idea that, I mean, the number of possible combinations and the number of hypotheses that you could generate grows very quickly, even for only one template, right? Particularly because I mean, here we have one where you could have an attacker setting different set points, and even if you discretize that, there's still a lot of options that you have. So, so that is one of the limitations. We've done an implementation of this. So we wrote a little Java framework that basically does exactly that. I mean, generate hypotheses and yeah, run them. I mean, so you take the templates in, you generate hypotheses. Then we have a thing called an orchestrator that basically runs an abstraction of the different tools that we have in the back end. They sort of each have an executor. And then this tree gets evaluated, and you get a risk assessment for each hypothesis, and then later you can rank them. So you basically get a sorted list of, hey, this is the thing that's most likely to happen right now based on the data that we have. What we'd like to do before the end of the project is actually couple that to our lab to run that against real-time data, because right now we're doing it against pre-recorded time series. And last slide. So I'm almost in time. So yeah, just quick summary. I mean, we're sort of investigating this concept of risk assessment by hypothesis testing across multiple domains. We have an early proof of concept. There's sort of two main issues that we have. I mean, one is, well, as you can see, with the present brute force approach that we have, these branch points, they don't really work very well. Or let's say we can see the limits of them. I mean, they work fine for us right now, but we can see the limits of them coming. So there is something that, I mean, kind of going forward, one would have to think of a non-brute force approach to resolve those. And the other one is that right now, because of simplicity, we basically limit ourselves to single actions by an attacker. So one of the open questions is also how would you combine an attacker that has attacked a system, and then of course he would be free to combine multiple attacks or more complex attacks. And so that's something we're not looking at the moment. But again, this is work. This is relatively early proof of concept work. So thanks.